Hello. This is video number 46. And for a little while now, we've been talking about graphs and specifically finding the shortest path in a weighted directed graph from a start node to every other node in the graph. But I've been walking through this invisible in thin air algorithm without actually stating what the algorithm is, but let's turn around and write all the steps down that we were following in those previous examples, last couple of videos. This is an algorithm, loosely stated. It'll all be pseudocode. Algorithm for shortest path, comma, given a graph, got to have the graph, given a graph and a start node. Now, are those parameters? I don't know. I mean, if you've got a graph class, maybe the graph is already in there and you don't pass it in or anything. You just operate on it. That would be sort of like the oil field or the maze, where you've got a graph stored internally and the main program just says, okay, do all that stuff yourself. Read yourself from a file, find the shortest path the way you're supposed to, do all that things for me, and get back to me when you're done. Start node, that could be built in with our particular implementation of it. But at any rate, we are going to try to find the shortest path given the graph and the start node. Okay. Need to do some initialization. initialize colon. I'm going to, well, I almost said this might go in the constructor. I'm going to quit referring to any kind of implementation stuff. Let's just talk about the steps that have to be done by somebody, somehow, somewhere, for each node in the graph. What do we need to do before we even start? We need to set the distance to 0. I'll abbreviate dist, D-I-S-T, and I'll underline it like it is an official variable, but you know, you could use any variable name you want. Set distance to, what did I say, to 0? Oh, good heavens, no. Then we're not going to find any shortest paths, are we? Set distance to infinity, which, of course, is not a number you can represent on the machine. There are different ways to represent that. We've already talked about that. Set frozen to false. What are those? Why do we initialize that to that and this to this? The distance is what we're going to try to incrementally reduce over and over until we end up with the shortest possible distance between our start node and every other node in the graph, one at a time. The frozen is whether or not the algorithm has already determined, you know what, that's the best we're going to do for that node. We can no longer improve it. There's no reason to even look at it anymore. So once a node is officially frozen, that means we know that we are not going to improve on the shortest path to that node anymore. Now I'm going to include up here in the initialization, after we've done all this, then we're going to need to turn around for the special case of the start node. That one, set start node's distance to 0. Why? Well, I hope it's intuitively obvious. The start node, if we're looking for the distance from it to itself, we don't have to go anywhere. We are already there. So its distance is 0. It's also going to get us jump started on the loop that's coming up here, like about right now. I'm going to draw a line here just to separate all the initialization stuff from the loop that's going to constitute most of the activity of the algorithm. And good grief, this is a long statement here. Get the next unfrozen node which I'm going to need to be able to refer to later, so I'm going to call it capital N. Get the next unfrozen node capital N with the smallest distance smallest dist. And I'm going to call that smallest distance capital D because I got to refer to that as well. I told you, that was a long statement. That's a bunch of stuff, and we haven't even started the loop yet. Get the next unfrozen node in with the smallest distance d. Well, that's what I meant by up here, this statement right here. Set start node's distance to 0. That's kind of jump starting the loop, priming the loop, like you read a value before you start testing to see if it's the sentinel. The start node will be the only one that has a small distance at all, because the others are infinite, and the start node's distance is 0. So the first time through, that's going to be the start node. Here comes the loop. While d isn't infinite, now we're going to have to talk about that. That might not be actually the best way to set up the condition for that while loop, because we might run out of unfrozen nodes. There might be a couple of things you want to test here, but I'm going to keep going, and then I'll save the discussion for later. While it isn't infinite, if I got a distance, let's look at these two pieces. I got the next unfrozen node in. Visualize node in with the smallest available distance. And let's say it's something like 0 the first time around. It might be 7 the next time around, whatever. That distance is not infinite, so we do have now the next node. Here's where we are in the grand scheme of things. We now have the next node for which we know the shortest distance to in the graph. That didn't come out English-wise very well, did it? We do have the next node for whom we know the shortest path. So now that we've got this distance d that's not infinite, it's not an infinite distance away, meaning we can get there from here, that what we need to do inside the loop is we need to, who is it? Node in. We need to freeze in. Why freeze in? We know about you in. At this point in the algorithm, we know that we have the shortest distance to you, node in. So we freeze you. Now, not only do we freeze you, we want to look and see if we can update all your nodes in your adjacency list. We want to see if we can offer them something better than what they already know. So another loop inside a loop. This could be a for loop because we're going through an adjacency list, or maybe that's a while loop as well. Stop, bad professor, stop talking about implementation. For each node, capital A, all these homemade variables on the fly, for each node, capital A, in node n's adjacency list. Now don't let all this stuff scare you. We've actually walked through every single one of these steps in 2 examples in the videos now. So all this stuff is just kind of a summary of what I was kind of doing in thin air and hand waving and filling in tables and filling in node traces and everything. For each node A, the adjacency list node A, in n's adjacency list, a couple of things. A test inside the for or the while, whatever it may be. If, a couple of things. Number 1, A isn't already frozen. In other words, there's still a possibility we could do better than what we've done already. And two-part condition here. If A isn't already frozen, and if we can improve A's distance, we can offer it a better distance to the start than it already knows about. A already isn't already frozen, and we can improve A's distance. Dist, an attribute or a variable. If that's true, then let's do it. We found one that we can offer a better distance to, and it's going to accept it. Set A's distance. This is the node in the adjacency list. Set A's dist to, what do we update it to? Well, we update it to the distance to the node that we just now froze, which is D. D is the distance to node N, which we're just now freezing. Update A's distance to D plus, I'm going to call this, make it look like a function. It's actually a label on the arc. The weight of node N to node A. That's the weight on that arc, N comma A. And I'll put that in square brackets so it looks like a single quantity. There. Set A's updated distance, since we've already tested it. Now that's actually this little formula here, this little expression, that's what we use to determine whether or not we could improve A's distance. If this quantity, the distance D to node N, plus that additional distance from node N on over to node A, if those two things added together are better than the distance that A already knows about, then we're going to upgrade or update A's distance to be this new quantity that represents the improvement. I hope this makes sense, since we were actually, believe it or not, we were doing all this stuff, filling in all that trace of all the nodes as we were tracing through the graph. One more thing before I forget, and I did forget actually, and I had to go back in when I was reviewing, I thought, well, this doesn't show up in there anywhere. Now it does. Set A's crumb is what I've been calling it. Sometimes I call it trail. I've got other names for it. I kind of like crumb, the fairy tale flavor to it. You know, we're leaving a trail of crumbs, how we got to where we are. Set A's crumb to N. That's the backward step along the shortest path we know about so far, backward toward the start node. Okay, so this was all an if inside a loop that's looping through the entire adjacency list. And now what? While D is an infinite, we've done everything we need to do here to, well, actually, I should probably include this if I'm trying to bracket off loops and fors and everything. There. Is that right? We're still inside the while loop, but we've done all this stuff. Now we've done everything we need to do to node N, including update any nodes in its adjacency list whose distance we could improve. What's the next thing to do? The next thing to do is this step again. Get next unfrozen node N with smallest distance D. Darby's snoring. Can you hear her? Probably not. You think, well, he's going to have to erase the board and fill it up again. Nuh-uh. This is it. That's the whole thing. That's the while loop. While D is an infinite. Now, this test here made me uncomfortable. This is a little complicated here. How do we know we need to keep going through the loop? We keep going through the loop, and you can phrase this any way you need to in your own implementation of this. But we got to go through the loop again if we find a node that's not frozen with a distance that's less than infinity. So there's actually kind of two pieces to that condition, that we keep going and keep going and keep going, as long as there do exist unfrozen nodes with distances that are less than infinite. If either one of those, if we run out of frozen nodes, we got to fall out of the loop. I'm sorry, if we run out of unfrozen nodes, we've got to fall out of the loop. If we run out of nodes that are unfrozen with distances that are less than infinite, then we fall out of the loop. The ones that are unfrozen that still have infinite distance, if that's the smallest value we can find, an infinite distance, then we can't improve on that. That means that that node is an infinite distance away. It's not reachable from the start node. So we're not going to be able to offer it a shortest path. And if you look at the example output in the program assignment, you'll see that it's just printed out, you can't get there from here. That's not reachable. And that could be possible in the graph, depending on which directions the arcs go and all that other sort of stuff. Ladies and gentlemen, I present to you, that's it. I don't have to erase the board and start over. That's the whole thing. Then all you got to do after this, all the paths will be set. They'll have not only the numerical shortest path distance, if you set the crumb field as you were going along, then you also can step backwards through that and find out what the shortest path is, actually, from the start node to each node in the graph. That's it. I hope that's all you need to know. Some of it might be, how am I going to write this in code? That's your job. I've done my job. I had one job. You got one job. You do it, and I'll see you online.